Hi, this is Dr. John Bergdorf. In this video, we're going to explore set builder notation. Set builder notation is a way to describe a set in symbols rather than just listing all of the elements. We've seen already that sets can be described by a roster, where you list all the elements, or by a general description. And set builder notation basically takes that idea of writing a description and takes it a little bit farther by introducing some very sophisticated notation. So take a look at the example we see right here, which should actually just be example 1, sorry. Interpret the following, and then you see this very complicated looking thing. So everything in here is shorthand, and I will explore what it means. So we know automatically that that symbol right there has to do with the set. So we're going to say the set. And then the way you read this is the set of all values of x. This symbol, this vertical line, can be thought of as shorthand for the phrase such that. So the set of all values of x such that x is an element of n, and n, that big N, you remember, is a natural number, so x is an an element of the natural numbers, and then finally, and x is less than 7. So it's a fancy way of saying the set of natural numbers that are less than 7. Again, the set of all values of x, and that's represented by this part right here, such that means such that, x is an element of n, and x is less than 7. In other words, it's all the natural numbers less than 7. That's pretty easy to relate to. The natural numbers less than 7 would be 1, 2, 3, 4, 5, and 6. And that's what we're talking about. So this is a good way to represent more elaborate sets, and we'll look at a few here. Let's read this in words first, and then I'll show you how we might be able to get at what this looks like. So in the set builder notation, this would be the set of all values of x, and that vertical line then again means such that x is given by a formula 4n plus 1, where the n is a natural number. So the idea here basically is you pick a natural number for n, you plug it into that formula, which is basically this, the x is equal to 4n plus 1, and it will generate the values of x that actually end up in the set. So here's how you do that, or here's how I would do that. I would make a little table, and I would pick my some values of n, and then from the formula, I would explore x is equal to 4n plus 1. The natural numbers are the counting numbers, the numbers you learn to count with from in school. So it's 1, 2, 3, 4, so forth. And if you take each one of those values of n and plug it into this formula for x, 4 times 1 plus 1, that's 4 times 1 plus 1, that'd be 5. x is equal to 4 times 2 plus 1, plugging in different values for the x. Keep the colors consistent here. 4 times 2 is 8 plus 1 is 9. X is equal to 4 times 3 plus 1. 4 times 3 is 12. 12 plus 1 is 13. And then finally, well, not finally, but next, x is equal to 4 times 4 plus, did it again, plus 1. 16 plus 1, 17. You're generating a set of numbers based on this rule in set builder notation. The elements of the set are these values, and they would continue on. So for example, we'll do one more here. If x is 5, or excuse me, if n is 5, x would be equal to 4 times 5 plus 1, that's 21. So the set A looks like this: 5, 9, 13, 17. And as you go, you may begin to realize what the pattern is. You're starting with the number 5 and basically counting by 4s. 5 plus 4 is 9, plus 4 is 13, plus 4 is 17, plus 4 is 21. The next number would be 25. And this continues on and on. Almost ran out of room for my set notation right there. 5, 9, 13, 17, 21, 25. So set builder notation allows us to describe a set in a pretty elaborate way. Let's do one more, kind of the same thing. We have the set of all values of x such that x is equal to n squared minus 1, where n is a natural number. So again, we're going to start with the value of n, just that natural numbers, and then we're going to substitute them into the formula n squared minus 1 to get the corresponding values of x. And we pick natural numbers, so we pick 1, maybe 2, maybe 3, 4, and 5. We plug those in and into the formula, basically. So x is equal to 1 squared minus 1. That would be 0. X is equal to 2 squared minus 1. That would be 4 minus 1 is 3. X is equal to 3 squared minus 1. That's 9 minus 1 is 8. Pattern's a little bit harder to see here, but I think we will see it. X is equal to 4 squared minus 1. 16 minus 1 is 15. And finally, or not finally, but the next one we'll do, and hopefully call it quits from here, 5 squared minus 1. 25 minus 1 is 24. Basically what you have is, in each case, the numbers you're getting are 1 less than a perfect square. So if I write that all out, we have 0, which is 1 less than 1 squared, 3, which is 1 less than 2 squared, 8, which is 1 less than 3 squared, 15, which is 1 less than 4 squared, 24, which is 1 less than 5 squared. And let's see, if that pattern continues, the next number we'd look at would be 6. 6 squared is 36. 1 less than that would be 35. And again, we'll continue on. And that's set builder notation.